No, no, no.
Clear.
Clear. When you it's okay to stick
Can I have your attention, please, everyone?
on this one.
Can I have your
And then you see it through, so you can't put another one on.
Then, can I have your attention, everybody? All right, so let's go on. A lot to cover today. Yeah, we're going to finish the electric potentials chapter. We're going to start capacitors. This is chapter 23 from Young and Friedman, right? And then this one is chapter 24. So that's where we are. I would like, as always, review what we have been doing. We have been doing the following: electric potentials and potential energy. We defined the electric potential between 2 points. We said it is minus integral of E dot dr, right? This is in general definition for potential difference. For point charges, we just focus on point charges. Then, if you have a charge here, little q, and you ask what is the electric potential at distance r from q, you can use the electric field for a point charge and then integrate it from some position to another, and then you can find the potential difference. So the electric potential for charge q at distance r away is V equals to K Q over R, and K is 1 over 4 pi epsilon naught. For simplicity, I'm just writing K Q over R. If we were to place another charge here at this point where the potential is V, let's call this new charge Q prime, it will have a potential energy. There will be potential energy associated between the two charges, and that potential energy is K Q1, Q2, in this case Q prime, divided by the separation between the which is R. KQ over R is V, so we get Q prime times V. So once you know the potential everywhere, the potential energy, if you place a charge in that potential, its potential energy would be whatever the charge value is times the potential at that point in space. Similar to electric field and force, if you place a charge Q in an electric field E, the force on it is Q times E, product of the charge. So this is for point charges. We also talked about parallel plates or infinite sheets, parallel plate capacitor, which we talked about more today. So for parallel plates, let's say this is the x direction, 0, this is D, and let's say this plate here is positively charged, this plate has a minus charge, and the electric field is in this direction, and it has E. Then the electric potential for parallel plates so far we're still reviewing, right? Electric potential for parallel plates was V equals to E times X, right? E times X. So the potential at the negative plate is 0, and the potential at the positive plate is ED. So the potential difference, the potential at the negative plate is 0. The potential at the positive plate compared to the negative plate is ED. Yes.
Do we also make our expressive value at the
It's easiest, yeah. So we got that. Let's see, what's the next thing? Then, yeah, we talked about spheres and spherical shells. What is the electric potential when you're outside? Yeah, they're similar to point charges. So spheres and spherical shells. So for here it's capital R. So for R greater or equal to capital R, the potential is just, let's say, charge Q, the potential is K Q over R with your outside. And that's it. Next, we're going to talk about. Yeah, let's apply this. We're going to use this for two examples, and then we will move on to the connection between the electric field and the electric potential. So let's do two examples here. Let's say I have a sphere of radius r, and let's say it is maybe positively charged. Somebody charged it, and they tell us that the potential V at the surface is 1,000 volts. The potential at the surface is 1,000 volts. So it's KQ over R. It just works out that K times Q divided by R, whatever they are, they just end up being 1,000 volts. So we're just told that. So now, here's the question. Let's say we have a proton. A proton we're going to place right here. Protons are positively charged, right? This is a proton. Let's say the initial speed is 0. Proton is initially here because an initial speed is 0. You let go of it, what does the proton do? What happens? Does it just get stuck? Yeah, it will. These are pluses, they don't want it. They will push it away. So the proton will move away. So it will be here, it will be here, it will be here, it will be here, it will keep moving away. So the question is this. When the electron is here, what's the speed? V final. And here means territory. When the distance, let's call it R final, is equal to 3R. It's 3 times the radius of the sphere. What is the speed of the proton then? So here, let me ask first, when R is equal to 3R, what is V? What's V meaning the potential there? I know at the surface, when little r is equal to capital R, it's 1,000. We're told it's 1,000. Okay, and at 3R, how much is it? We said KQ over 3R. So compared to 1,000, it would be, yeah, it would be 1,000 over 3. It would be 1,000 over 3. So let me show you, let's just be sure we're on the same page. The initial, the potential initial is K Q over R, right? And that happens to be 1,000 volts. The final, the potential final, these capital V's with little bars stand for potential, right? Little v is speed. Would be KQ over the distance, but the distance now is 3R. So it is 1/3 of this. Which is 350. I will leave it like that. So far, we're good? Mm-hmm. So, our goal is to find the speed of the proton. So, when I say a proton, obviously you're given the charge, right? It's little e, 1.6 times 10⁻⁷, and you're given the mass, right? So, so how are we going to find the speed there? Newton's laws or conservation of energy? Conservation of energy says the kinetic at the beginning plus the potential at the beginning. Okay, kinetic at the end plus potential at the end. Kinetic at the beginning plus potential at the beginning. Do we have any kinetic energy at the beginning?
No.
So that one is zero. Any other zeros or no? The potential energy is not zero. Okay. So the kinetic energy at the end is equal to the potential at the beginning, U initial minus U final. How is potential energy related to potential? QV, right? Yeah, QV. So it would be the potential energy at the beginning is just the charge of the proton, which is little e, times the potential at the beginning, which is capital V initial, which is 1,000. Minus the potential energy at the end is the charge, which is again little e, times the potential at the end, which is capital V at the end, which is 1,000 over 3. So we just get E times V initial minus V final, which is E times V initial minus V initial over 3, right? It's a third. V final is 1/3 of that, and then so 1 minus a third is 2/3, right? So we simply get 2E over 3 V initial. So that's the kinetic energy at the end, which is 1/2 mv squared. So let me write it this one. 1/2 m little v final squared is equal to 2e 2/3. So the speed at the end, speed is going to be multiply both sides by 2, divide by the mass, so you get 4 little e over 3m capital V initial, and we have to take the square root. So we need to plug in the numbers. You can plug them in. So 4 little e is 1.6 times 10 to the minus 19. V initial is 1,000, right? And then I have 3, the mass of a proton, 1.6 times 10 to the, 1.67 times 10 to the minus 27. You do the numbers, I will just give the result. It should be 3.57 times 10 to the 5th. So that's the speed at the end. So the next question is going to be similar to this, but kind of reverse. I will explain. So again, I will just spare the details. You plug it in. So let's go to the next one, which is example 2. Go here. Let's consider a solid sphere. Or a spherical shell with radius r. Okay. Radius r. And we're going to put plus charge here. So we're going to place plus charge. The total charge is going to be Q. It's going to be capital Q. And it's going to be 100 nanocoulombs. That's the total charge from the sphere. The radius of the sphere is going to be 0.5 millimeter. So 0.5 millimeter, that's 5 times 10 to the minus 4 meters. That's the radius of the sphere. Okay. Nothing going on yet. So you got a sphere and it's charged like so. I'm going to make part A for this. Find V at the surface. Find the electric potential at the surface. V. So what should we do?
KQ over R.
KQ over R, good. Okay, so let's do it. You can plug in the numbers. K, U, over R. K, as always, 9 times 10 to the 9. Q is 100 nano times 10 to what power? Yeah, times 9. And then R is 5 times 10 to the 4. So minus 9, positive 9. Okay, so you have 9 times 10 to the, becomes 10 to the 6th over 5. 9 over 5 is 1.8, right? 8 times 10 to the 6th volts. So that's the potential at the surface of the sphere. We're going to, so nothing is going on yet, so you just have a sphere that's charged, all right? Then we're going to add something to it. And something we're going to add is a proton, but the proton now is approaching. So suppose we have a proton, initially it's here. The proton is very far away. It has some initial speed, V initial. Okay. So very far away means what? Very far away, yeah, infinite, yeah.
Would there ever be a problem where we have to figure out how close it is?
So, yeah. So the question is, so you're told the following. You're not given the initial. So the proton starts very far away. And as it approaches, will it speed up or slow down? Slow down because they're both positive. So it slows down and slows down and slows down, and they tell you by the time it arrives, it has 0 speed. So it barely touches. Gets to here. As you can imagine, so when it gets to here, V final is 0, right? And the speed is 0. What does it do afterwards? It will go back. Yeah. We're not interested when it goes back. We're just interested in the fact that it came from very far away, infinitely far away. And by the time it gets here, the speed is 0. So what's the initial speed? That's the question. Newton's law is conservation of energy. I think, yeah, conservation of energy. When we say kinetic at the beginning plus the potential energy at the beginning is equal to the kinetic at the end plus the potential energy at the end. What's the kinetic energy? Are there any zeros here?
Yeah.
Which one?
The I and the KF.
So the kinetic energy at the beginning, at the end is 0, right? Because
Yeah.
it's barely moving. It will stop. And the potential at the start, yeah, very far away. The electric potential is 0. So QV is 0. So the potential energy is also 0. So this one is 0. So the kinetic at the beginning is simply equal to the potential at the end. Kinetic energy became potential. Kinetic at the beginning is 1/2 mv initial squared. I guess I'm calling, that's okay, yeah. And then the potential at the end is the charge of the proton, which is Q or E, and then the electric potential at the end. So V D initial would be twice E over M B final. Oh, here I called it initial with an I, and here I called it initial with a non, but obviously I mean the same thing. So plug in the numbers. Let's plug them in for us. So 2, 1.6 times 10 to the minus 19. What's the potential?
QV.
Yeah, the potential is this, right? V final, it ends up here at the surface, but what's the potential at the surface? It's this. Yeah, so we already found it. It's 1.8 times 10 to the 6. 1.67. So 1.86 times 10 to the 7. Very fast. We're going to continue, but there's one little topic I would like to just mention quickly, and then we're not going to make much use out of it. So, but I just want to mention it because just to be complete. That's the everybody's favorite, the dipoles, right? Oh. Okay. So here is a dipole. Dipole always points this way, right? P. The magnitude is the charge times the distance, QT. Do you remember the torque on a dipole if it's in an electric field, E, some uniform field? So tau is to P cross E, right? Yeah. Now, let me ask you the following. I'm going to give you 3 situations, and I ask you what situation has the most potential energy, or more energy in your estimation. So here is the first one. So in all of these cases, the electric field is to the right. The electric field is this way. In the second situation, E is this way. And in the third situation, the electric field is this way. Okay? In all cases, the electric field. First case, our dipole is this way. Second case, our dipole this way. Third case, our dipole this way. First case, the dipole points left, up, to the right. Which case is the most, let's say, stable? Yeah, this one, right? Because remember with an electric field this way, imagine that wall is plus, this wall is minus. So the positive is where it wants to be, and the minus is where it wants to be. Plus wants to be as far away from the plus as possible, that's there. And the minus wants to be far away from those minuses, so it wants to be here. So it's stable here, nothing is going on. In here, it will flip, right? And it will align itself with the electric. For this one, if it's exactly at 180, it will sit there, but it's unstable, right? Stable. But the moment we tilt it slightly up or slightly down, what does it do? It goes this way. So it's actually here it has the most potential energy. Sorry? Yeah, at this point, the dipole has the most potential energy because, so think of this piece of chalk. If it's here, there is a chance it will fall. If it's at the table, there's a chance it will fall to the ground. But if it's already on the ground, does it jump by itself here? No. So this one is the least potential energy because it's already aligned with the field. For this one, if you let go of the dipole, it will flip, right? It will turn. Yeah, and then go that way. This one, the moment you tilt it maybe slightly up, disturb it up or down, what does it do? It turns. So this one is the least stable. Right? This one is the least stable. This case. So which one has the most potential energy? Let's think about it. Imagine it's already aligned. This is the minimum, right? So somebody has to do work to twist it this way. I have to do work to twist it this way. And then my work is not wasted, it becomes potential energy. So now it has potential energy. When I let go, what does it do? Rotate. And then I have to do even more work to take it from here to here, right? I have to force it to come all the way here. Now here it has the most potential energy. How much work did I do is equal to the potential energy at that position. I go through the derivation of the notes. I don't want to go through it in class because it will take 20 to 30 minutes, but I don't have the time to do it. About 20 minutes. So I'm going to just state the fact or the result because we're not going to use it much at all. So here is the potential energy. It says it's minus P dot E, the dot product. And as you know, the dot product is like this, minus P times E times the cosine of the angle. Or shortly, in short, it's just minus PE cosine of theta. P is the magnitude of P, and E is the magnitude of E. So P is a positive quantity, E is a positive quantity, and then you get the cosine of theta. So that's the dot product. So let's look at all of these. In the first case, what's the angle in this case? What is theta here? Yeah, theta is 0. So what's the potential energy here? Not quite 0. It'll be what? PE minus PE. Right? And here, cosine of 0 is 1, so it's just going to be minus PE. Let's look at in this situation, it's minus PE. How about in this situation? Theta is 90, okay? And then I heard what? U is 0. Cosine of 90 is 0. So we just get 0. How about here? Theta is 180. Yeah. So cosine of 180 is minus 1. So it's just going to be P times E. Which one has the most potential energy? That one is the most positive. This one is 0, but 0 is still more than negative. So that's all I want to say about this. Okay, we're going to let's see. Next topic is going to be the relation between the electric potential and the electric field. Or more precisely, I should say this. Given the electric field, we know how to find the potential, don't we? In principle, given the field, integrate it to get the potential. How about the reverse? Given the potential, can we get the field? The answer is yes. And in summary, before we even go through the result will not be surprising. You integrate the field to get the potential. So what do you do to the potential to get the field? Yeah, differentiate it. That's it. So so the result will not be surprising. That's what we will get. So given V how do we get E? So delta V is the integral of dV, which delta V is minus E dot so now, in general, E can be written as this, as an x component of E in the I hat direction, plus some y component of E in the j hat direction, plus some c component of E in the k hat direction, right? E can have three components, right? X component, a y component, and a z component. Questions? Reasonable enough? Okay. How about dr? How do I express dr in terms of like dx I hat plus what? dy j hat, right? Plus dz k hat. Let's do their dot product. Dx, right? Or dx dx, yes. Good. Dx plus dy plus dz. Is everyone clear on the dot product there? Dot product only, because I hat dot I hat is 1. I hat dot j hat is 0. You can't cross. You don't have the cross terms, they're not there. Just you would just have the ones, the I hat goes with the I hat, j hat with the j. That's the dot product. And remember, E dot d, dv is negative E dot dr. Can you see that? dv is minus E dot dr. So E dot dr is equal to minus dv. So far, we're just playing with symbols. Let me ask you a question here. If you have a function f of x, just a single variable, here is f of x. How do you find df? What's df? How can you? It's df dx dx. Yeah. That's the differential df. And how about if you have a function of more than one variable? If, let's say you have a function, let's say v. Let's say if for a function v that depends on x, y, z, what's the total differential dv?
Partial derivative.
Yeah. Good. I know you have to pick up. So now let's compare this one, this one. So what do you notice? Or let me write them side by side. So I get this. This is dv, it's there. And let me write below it. Here is dv also. dv is this, right? Or the negative of that. So let me write them below each other. It's also equal to this. Minus dx minus EY, minus EZ, right? So what can you say about EX?
It's equal to negative, partial derivative d of dx.
Yeah. How about EY?
Same.
Yeah, easy. So let's write that down. So we get this. So you notice that EX would be minus ED dx. EY would be minus ED dy.
The partial conversion over
And
partial dx the partial partial semua berarti ini seperti dx oh bukan partial.
So let's write the electric field vector now. So E, so I'm back to here. But I'm going to replace EX by, right, so in this formula here, yeah, by this, yeah. So, yeah. So I would have EX is going to be minus dV dx, that would be I hat. And then EY is going to be minus dV dy, okay? Minus K hat. So this is minus dx I hat plus dV dy J hat plus dV dc K hat, right? And this is the same as minus. We can think of V as being factored in front. We have dvx I hat plus dvy J hat plus dvc. And this thing here has a short end there. Starts with a G, yeah. Gradient, yes. Yes, it's a triangle, inverted triangle here. Looks like that. Minus gradient of so if it's just a function of one variable, then the electric field is just the derivative. Let's say dV dz, dV dx, with a minus sign. So back to what I stated earlier, you integrated E to get V. So you have to differentiate V to get E, that's all. So we could have predicted this result, right? Okay, so here is an example. Given, here's V. Is equal to A, let's say x squared, y